Okay. Yeah. All right. Next up, we have Mark Koch. He's going to talk about Guppy.
Yeah. Thank you, Alex. I want to start this talk going over some, I guess, recent-ish news. Namely, I think 1 month ago, the Unitary Fund came out with the results of their yearly quantum open source software survey, where they ask people all sorts of questions regarding to quantum software. And for programming language people, I think one of the most interesting questions is which languages do people actually use when they do quantum stuff? And maybe this is not super surprising to you, but as it turns out, Python absolutely dominates this field year over year. In fact, if you're a quantum hardware provider, you're pretty much expected to offer some interface in Python to interact with your device, because this is just what people use. So, like it or not, I think Python is, at least in the near to midterm, here to stay one of the major players in quantum. And I have a small, non-exhaustive list of existing Python frameworks that are out there to do quantum computing. And the current state of play, pretty much across the board, looks roughly like this. Right? I'm sure you've seen this before. We construct some circuit object, and then we call some functions on it to add gates to a circuit. I mentioned there's a few frameworks out there that go a bit beyond that, but I'll get back to those a bit later. You'll notice that this way of going about things is fairly low level. Right? We have languages like Q#, which is at a way higher abstraction level, but in practice, this is what most people are using today. But as many of you know, at some point you run into some issue if you stick to this circuit builder approach. For one example we've been thinking about quite a bit is this repeat until success algorithm pattern that Craig has also already mentioned in his talk this morning. And just to reiterate, the rough idea is we want to apply some operation on a register of qubits, and we do this by allocating some inciders, acting on the register, and then measuring out the inciders. Then we look at the result. If we get some desired outcome, then we're done. We know we've performed the action we wanted to. But if we get some undesired outcome, we have to apply correction, and then we just try the whole thing again. Right? We keep going and going until we succeed, which is also where this name comes from. Now, the remarkable thing in this algorithm is that we do a measurement in the middle of the circuit, which then completely alters the control flow of the remaining program execution. And this offers some fairly interesting challenges related to how do I express something like this, how do I compile it, and how do I optimize it. And in recent years, people have started to get really interested in these things. Just a quick example. This is a paper from last year by Continuum Microsoft, where they looked at how do you compile these sorts of programs at the backend level, and how do you actually run them on actually quantum hardware. But getting back to what I said before, if you wanted to express something like this in this circuit builder pattern, you're going to have a hard time. I'm sure you can come up with some abstractions to express this, but it's not going to be nice or intuitive. Because if I were to explain this algorithm to someone, what they would want to write is a loop, because that's the kind of intuitive representation of these things. And this is where Guppy comes in. What we try to do with Guppy is give people the best of both worlds. What Guppy is, it's a high-level quantum programming language that looks just like Python. Right? So we're targeting people who really like Python and kind of the Pythonic way of programming, but who also want to use some of these more fancy features like mid-circuit measurement, classical control flow, and so on. In fact, since we want people to actually use Guppy, we go one step further and say it doesn't just look like Python, it's actually embedded into Python. So there's a very tight integration between this new Guppy language and what people are already using in Python, which is really convenient because people can just reuse the existing Python workflow if they use external libraries or data processing Python. This all will just work. I want to start by just going over some very quick examples to give you a feel of how programming Guppy feels like. The nice thing about Python is that most people know it, so the syntax should be fairly clear, I hope. But the way you define operations in Guppy is you just write a function that looks like a regular Python function, except you stick this add Guppy decorator on top. So in this example here, we're defining a function that takes one qubit as input and an extra float as input. Then we apply a Hadamard, RZ, and another Hadamard on the qubit, and then we return it. Now, like any other embedded language, Guppy programs are defined in an outer host program, which in our case is a Python script. Right? So we're actually in some example.py file here. And we have this Guppy-lang package in Python where we get this decorator from. And the nice thing about being embedded in Python is you can mix and match Guppy code with any old normal Python code. And this opens up some interesting possibilities of making these worlds interact in some way. But I will get back to that a bit later in my talk. One thing you always need in Guppy is a main function, which is the entry point to your program. And in this example, we're just allocating a new qubit. We're calling the function you've just defined, and we measure the result and return it. And once I've defined all my functions I want, I can just call guppy.compile and get my compiled program back. Right? And then I can run it and get some result. At the moment, we're linking this against a quantum simulator, but in the future, you'll be able to actually run this on a quantum device. I'll also point out that this is still a bit work in progress, this execution part, this last line here. I think we have 1 or 2 laptops at the moment that are set up to run Guppy. One of them is in Argentina at the moment, so I can't demo it right now, but we are hard at work to make this run. Also, a very important thing to point out is what this execute thing is not doing is we're not just taking the Python interpreter and we run this code. This is not what's happening. Namely, this program thing we get out is actually a standalone executable that I could save somewhere, I could send it to a friend, execute it at some other time, completely independent of the Python environment. Right? And this also means that the thing that's actually happening when I call compile is we're looking at the source code in the Python file for all functions that are annotated. We parse it into an abstract syntax tree, and then we compile it from scratch. So this means the only thing we're actually inheriting from Python is its syntax. And everything else is completely custom. We can decide whatever we want to do. Right? And in this sense, we try to strike a balance between offering a language that looks and feels like Python, but maybe in some aspects behaves a bit differently, depending on what is most suitable for our quantum domain. In that sense, we're also a bit different from these other frameworks out there that I've mentioned before. So Catalyst by Penny Lane, AutoCasm by Amazon, and Blocks by PLanQC'. Because what they're doing is they might do some AST transformation beforehand, but in the end they rely on tracing the Python interpreter to construct a program representation, whereas Guppy is completely divorced from Python. Right? It's just embedded in the sense that we hijack its syntax. This is a very basic example to show you the true power of Guppy. I've prepared an example from this paper I showed you before that does repeat into success. So what we're trying to do here is apply this single qubit V3 gate on qubit Q using 2 ancillars A and B. Right? And the way we would write this in Guppy is we define a function that takes this qubit Q as input and also a number of attempts we want to try because we don't want this to run forever, right? We want to terminate. And then we just run a for loop, right? Just like you would do it in Python. Then we allocate 2 ancillars in the plus state. And the way this example here works is you can actually split this circuit in 2 parts and first only run the top part. Right? So we can do this like this, and then just measure out qubit A. If we don't get the result we wanted, we can just throw B away and continue, so try the whole thing again. If we succeed, we just implement the bottom part of the circuit, measure the second ancillar B, and if we get the result we wanted, we can break out of the loop, and we're done. And if not, then we apply some correction on Q, and we loop again, and at the end we return. Right, so what this shows is, I think my claim is that this is how, if I were to explain someone what this algorithm does, this is how they would implement it. So I think it's like the most natural way to write it, which is just how Guppy does it. I mentioned that we try to follow Pythonic behavior, but in some senses Guppy is a bit different than Python. Because Python is a fairly unsafe language. What do I mean by that? This code is perfectly fine in Python, but if you were to run it in the case where this V is false, you just get a runtime error because X is not defined. And it would be very annoying if you were to run into such a stupid error on your quantum device where it's been queuing for a few hours. So if you try to pass this code by the Guppy compiler, it will start shouting at you and say, no, if you try to use a variable, you have to make sure that it's actually defined. Right? And similar thing happening here. In Python, it's perfectly fine for a variable to have different types depending on control flow. But in Guppy, again, this is not allowed. If you use a variable, you have to make sure that it has the same type, no matter which path you took to get here. Speaking of types, Guppy is a strongly typed language. Like, unlike Python, where typing is pretty optional, in Guppy, your programs have to type check, and if they don't, they don't compile. Which is also why in all the examples I showed before, I had these type annotations for inputs and return types, since they're also required to do this checking here. And one nice thing this spices is that we can do linearity. Right? So we can make qubit a linear type, and then catch errors like these where you try to use the qubit twice, or you implicitly discarded the qubit here by not assigning the return value. And while these examples are fairly basic, this linearity checking works across any control flow you could write. To write some interesting programs, we also need some data structures. At the moment, in Guppy, we have tuples and lists, but I'm mainly going to focus on lists here, since it's the more interesting case. And also, fair disclaimer, the kind of runtime behavior of lists is still a bit work in progress, so we're hard at work here. Normally in Python, lists look like this, so a sequence of values, and then I can call functions like length on it, which give me the number back. But we could also imagine to have a list of qubits. And since the qubit type is linear, we would also expect lists of qubits to be linear. But in this example here, we would run into some issues, because if you would imagine axis to be a list of qubits, if we actually pass it into this length function, we have a problem, because this consumes the list, and then we couldn't use it afterwards because of linearity. So we actually have a different list interface for linear stuff. We call these lints. And in this case, you can see the length function actually gives me back the list so I can use it afterwards. But still, there are some kind of interesting issues with this. Namely, if I were to take this and give it to a Python programmer, chances are they might come up with something like this. So what am I doing here? I have two indices, I and j, and I try to apply a CX gate on my qubit register Qs at this index. Okay? And I'm even writing it back. So this looks innocent enough, but it's actually a big no-go in terms of linearity. Kind of the level 1 problem is to use Qs multiple times on the right-hand side here, right? But even if kind of your compiler is smart enough to understand, okay, I'm actually only using the qubit at this index, it's still not okay, because the compiler would need to prove that I and j are not the same for this to be valid, right? And this is undecidable in general, so not feasible, which points to the kind of broader issue that indexing into lists like this is not a linear thing, which is where I just say, no, you can't do this. Of course, people still want to do these kind of things, like argue with indices, and that's why we add this special higher order apply function that kind of does more the same thing as the line above. But here, in the case where I and j are the same, you just get a runtime error. But in terms of linearity, this still works. So that's kind of your way out. If your programmer says, I know what I'm doing, I want to reason with indices, please let me, you can do it on your own risk using this high order function. On the classical side of things, this is still a bit work in progress. At the moment, we only have immutable versions of these lists, because we're still looking at allocation and garbage collection things, but we're hard at work here as well. One thing we can also do is use Pythonic list comprehensions, which are quite neat. In particular, this doesn't only work for lists, but we have arbitrary iterators, or you can do zips or enumerates and so on, which all works. Which is also very nice in the qubit case. For example, here, what this does is just apply a Hadamard to every qubit in my register. Of course, in the linear case, you can't have these if guards, because it would violate the linearity of qubits in this case. One thing we want to add in the future is a notion of user-defined types, preferably using Python's class syntax, and then also allow users to define custom methods on these types. One thing I kind of teased at the start is by virtue of being embedded into Python, we might have some kind of possibility to interoperate, have some compatibility between these layers. And the way this works in Guppy is, let's say I'm in Python and I'm using NeverX to construct some sort of graph. Then I can actually use this graph in my Guppy function. I want you to focus on this bit here. We have this special pi expression in which you can actually refer back to variables which are defined in your outer Python scope. Right? And the way this works is, at compile time, we're just evaluating this expression and inserting the constant value into the program. And then what we're doing in this example is we're just iterating over the edges in this graph and construct a graph state. Of course, this only works if the type we're inserting is actually compatible with Guppy. Right? You can't just take any old Python class. There needs to be, like, there's restricted sets of types this works with. But in these cases, this works flawlessly. One nice thing this also buys us is interoperability or compatibility with other, like, classical circuit builder frameworks. For example, what I'm doing here is I'm constructing a PyTicket circuit in the classical kind of builder pattern, and then I can actually use this circuit in my Guppy function by loading it in using this Pi thing, and then we get out a function from qubits to qubits that we can call just like any other function in Guppy. And then finally, I want to talk a bit about what's going on behind the scenes, how we actually compile Guppy. Namely, Guppy is compiled to a new intermediate representation called Hugger, which stands for a hierarchical unified graph representation. It's sort of a sister project to Guppy that's developed at Continuum, and it's kind of a new IR for quantum classical programs for optimizing kind of between these domains. So the way we represent graphs in Hugger is as data flow graphs. So the way this works is nodes, boxes represent pure function calls, and then the edges represent data dependency. And then you notice these special boxes here. This is a condition box which executes either of the two paths depending on which thing has been plugged in on top. Right, so this is a structured way of adding control flow to data flow graphs. We have similar constructs to also explain kind of looping and so on. This is also where this hierarchical word comes from, because as you can see, nodes can themselves contain child graphs, and you can nest this arbitrarily deep. Now, if you want to learn more about this, you can head to our GitHub over there and have a look at this spec. Highly recommend it. There's some interesting stuff in there. Once we get this Hugger, we optimize it using version 2 of our new ticket compiler, which tries various things to optimize this. This is also we're hard at work to improve this and offer some good optimizations on these Huggers. And then afterwards, after we have optimized it, we further lower it to some QIR LLVM thing using an MLIR pipeline. But again, this is still a bit work in progress at the moment. Okay, so looking forward, Guppy is on a very active development. We are looking forward to add many new features. For example, we're working on adding more higher-level quantum abstractions, things like uncomputation or quantum control, and also things on the classical side, like adding more support for Python's classical types, and also your users to define their own types. We also have some, I guess, more crazier ideas in research directions, maybe adding a sort of qubit reference concept to escape linearity or suspend it temporarily, which we've been thinking about. And then like utility features like adding a language server and debugging. So if you're interested, you can pip install Guppy like this, and you can check us out on GitHub. It's all open source. Thank you.
Thanks. We have time for just one or two quick questions. Somebody? Yep.
So it seems like lists provide a lot of opportunities for violating linearity. Mm-hmm. What can you do besides this I see you can do a list comprehension and put that
Yep.
into a list. Subject to restraints. You can do the supply function, but that's
Yeah, it's
saying, hey, we
unsafe,
might
yeah.
break linearity. Is there other interesting stuff you can do with these lists?
I guess you can take stuff off them, right? I can kind of uncons or cons them. Take stuff off from the start or the back. But if you try to index into it, that's where problems begin, right?
Mm-hmm.
Other questions? I was wondering about the deployment on. Thank you. I was wondering about deployment on.
Okay, to real quantum hardware,
Yeah.
do you plan to compile it down to QASM or to, I didn't know about this QER intermediate representation. Is that executable on quantum hardware?
Yeah, so QR is also the thing that Q# compiles down to, but it's kind of, there are different profiles of what you can do with it. QR is essentially LLVM with like special types and operations that correspond to quantum things, but yeah, it depends on what profile you have, what the device can do, if you can execute it. So that's definitely one pathway. QASM3 is also possible, can also express kind of similar looping things that we're using here, but yeah, we haven't decided yet what the kind of final thing. This is the thing we're pursuing at the moment to get execution working in kind of the medium term, to also link a simulator in and so on. But yeah, many avenues to explore.
Okay, thank you. Thanks, Mark.